Hi, in this video, I will be showing you problem number 17 of chapter 15, section 9. Use the given transformation to evaluate the integral. Double integral over r, x square dA, where r is the region bounded by the ellipse 9x square plus 4y square equal to 36, and the transformation is given by x equal to 2u and y equal to 3v. So first, we have to use the transformation to evaluate the integral. So in order to apply the transformation technique, we have to understand what we mean by the Jacobian of the transformation. And we will also see how it could be applied in double integral before we actually do the problem. So transformation must be used. The given transformation, the transformation is x equal to 2u and y equal to 3v. And the given region is bounded by the ellipse, planar ellipse, 9x square plus 4y square equal to 36. Now what is a Jacobian? If a transformation T is given by x equal to x of uv and y equal to y of uv, what is the Jacobian of T? The Jacobian of T is J equal to dou xy over dou uv, or in other words, partial derivative of xy with respect to u and v is given by determinant dou x over dou u, dou x over dou v, dou y over dou u, dou y over dou v. Keep in mind this Jacobian is a determinant, and when I say dou x over dou u, I mean partial derivative of x with respect to u, with respect to u, partial derivative of x with respect to v, and so on. So if you apply the technique of expanding the determinant, you get dou x by dou u times dou v by dou v minus partial derivative of x with respect to v over times partial derivative of y with respect to u. Next, how do we apply, how do we change the variables in a double integral? We change from an integral in xy to an integral in uv by expressing x and y in terms of u and v and writing d of a as the Jacobian that we just discussed with this j, or partial derivative of xy with respect to uv, times du dv. That is dou xy over dou uv, absolute value of that, times du dv. So in the double integral, when the Jacobian is used, you have to always take the absolute value of the Jacobian. So it's always positive. Thus, the appropriate conditions in double integral over r, f of xy dA would be equal to double integral over s. So the way s is the domain in the uv plane and r is the domain in the xy plane. So it is double integral over s, f of x of uv, y of uv times absolute value of the Jacobian, absolute partial derivative of xy with respect to partial derivative of uv times du times dv. Now for our problem, here x is given to be 2u and y is given to be 3v. So we are going to first determine the Jacobian, which is dou xy over dou uv, which is partial derivative of xy with respect to uv. And if we take the determinant of that, in fact, I'm going to call this one as determinant of the Jacobian, which is equal to that, determinant of absolute value of the Jacobian is absolute value of the determinant that we are going to do, So it is absolute value of, it is dou x by dou u would be 2, first row. Then dou x over dou v is 0. Dou y over dou u, dou y over dou u is 0. Dou y over dou v is 3. So that is, the inside one is the determinant. Outside one is showing the Jacobian, absolute value. So this is equal to 6. Now, the integrand is x square. So in the new transformation, it is 2u the whole square, which is 4u square. Given the region to be a planar ellipse, which is 9x square plus 4y square equal to 36. If we apply the transformation that x equal to 2u and y equal to 3v into this ellipse, we get 9 times 2u the whole square plus 4 times 3v the whole square equal to 36. This would give us 36u square plus 36v square equal to 36, or u square plus v square equal to 1. So ellipse in the xy plane becomes a convenient disk in the UV plane. In other words, the planar ellipse 9x square plus 4y square equal to 36 is the image of the unit disk, which is u square plus v square less than or equal to 1. The moment we see the domain to be a disk, polar method, polar conversion will be the best method. So double integral over r x square dA is double integral over u square plus v square less than or equal to 1. We already got x square to be equal to 4u square from the step. So 4u square times Jacobian, absolute value of the Jacobian, which is absolute value of 6, times du dv. So double integral u square plus v square less than or equal to 1, 4u square, Jacobian is 6 that we found out, du dv. So taking the constant out, as the integral is over the disk, we can apply the polar, converting to polar coordinates. We get double integral over r x square dA equal to 0 to 2 pi, 0 to 1 because it's unit circle. Then it's 4u square times 4u square cosine square theta times r dr d theta. dA changes to r dr d theta. So inside the integrand, it is going to be x square, u square. So we have 24u square. That u square changes to r square cosine square theta. So it's going to be 24 r square cosine square theta. Then dA changes to r dr d theta. So now pulling the constant out, also noticing all these are separable functions, we can consider theta integral and r integral separately. Just 24 integral 0 to 2 pi cosine square theta d theta integral 0 to 1 r cube dr. So just 24 times I1, we are going to evaluate that separately. Integral cosine square theta d theta times r to the power 4 over 4 between 0 and 1. So we get 24 times 1 over 4 times I1. So it is 6I1. We'll evaluate I1 separately and put it back into the step. Plug it back into the step. So I1 is integral 0 to 2 pi cosine square theta d theta. Using the formula cosine square theta equal to 1 plus cosine of 2 theta over 2, double angle formula, we get 1 half theta plus sine 2 theta over 2 between the limit 0 and 2 pi. So which is half of 2 pi, the rest becomes 0, it's equal to pi. Substituting back into the step A, double integral over r x squared dA would be equal to 6I1, which is 6 times pi. In the next, we would also be doing one more double integral by using this transformation method or change of variables method. Watch my next video for problem number 23 and hope this video helps.